Section 22.7, the electric generator. So how does an electric generator works? Well, it turns out it works in the exact opposite way as an electric motor, which we previously learned about. An electric generator can produce an EMF, and where the motor took an electric current to turn something to cause a rotation, the generator takes a rotation to create a current. Let's take a look. So down here we have a coil that's rotated by some mechanical means. It's gotten spinning, right? But the key is that this coil is between two ends of a permanent magnet. So it's in the presence of a uniform magnetic field. As that coil turns, the angle of the magnetic field piercing that coil changes, right? We get different angles as it rotates with time. That means we have a changing magnetic flux, and if we have a changing magnetic flux, we will induce a current in the coil. That current can then be sent out, say, to power a light, which is pretty amazing. So let's take a closer look at how we can calculate the amount of EMF that is generated here. So if we go back to our motional EMF equation, that the EMF is the perpendicular velocity times the magnetic field times the length. And here, because the angle is changing, the motion is not always perpendicular to the magnetic field. But what we can write instead is for the V perpendicular, we can write this as V times sine of theta, where theta shows how the angle is changing with time. So it's a little more thorough as a way to write it. But we can take this one step further, and since we're talking about rotation, we can go back to our rotational chapter. If you'll remember way back in chapter 8, where we saw that the tangential speed is equal to the radius times the angular speed, omega. And that radius, if we're dealing with a rectangular coil as shown here, is just half of the width. So the width divided by 2. So if we plug that in, we would now have V times L times W divided by 2 times omega, super curvy W, sorry, those are so similar, times sine of theta. But this length times width is just the area. So that simplifies things down. Right, so we have the magnetic field times the area divided by 2 times omega times sine. And what we can do with the sine is remember that our theta, our angular displacement, can also be written in terms of our angular speed times time. Remember, theta is equal to omega times t. Or the other way that we saw it, that this originated from, was that the angular speed was the angular displacement of theta divided by time. So here we're just assuming our initial time and our initial angle are 0. So instead of sine of theta, we can write this as sine of omega t. And this will give us the EMF for 1/2 of the loop. But remember, the loop is more than just 1/2. There are 2 halves to it. So we need to multiply all of this times 2. And then to be more general, we can say, well, we assumed that there is just one turn, but there could be many turns. There could be n turns. So we multiply by n as well. Write that a little clearer. There we go. So the 2's cancel out. And what we're left with is that the EMF is equal to the number of turns times the area of the loop, which we derived for a rectangular loop, but it could be a circular one. The exact shape doesn't matter. Times the strength of the magnetic field, times the angular speed of that turning, times sine of the angular speed times time. Since this is a function sine of omega t, we could plot how the EMF changes with time. It starts at 0, goes up to some maximum value, back down to 0, back to that same maximum value, but with the opposite polarity, oriented in the opposite direction, back to 0, and back again. This looks like our AC voltage that we previously saw. And it's created just by having a coil that turns in the presence of a magnet. So what we'll call that peak voltage, that maximum value, we'll call that EMF naught, right? Where EMF naught is equal to everything in front. The number of turns times the area times the magnetic field times that angular frequency or angular speed, omega. And the rest is sine of omega t. Rather than working with angular speed or angular frequency, it's often easier to work in terms of the cyclic frequency, right? Which is turns per second or cycles per second. So we remember that omega is equal to 2 pi times our cyclic frequency f. And so this is the equation for how we can calculate the EMF that is induced in a rotating planar coil. Now, where does this actually apply? Well, this is the basis for power stations, for electric generators, like Moss Landing. Moss Landing power plant works in this way, where there's a turbine. It's usually powered by steam. So you might need to burn something. Some are, you burn coal, others natural gas, but you create steam. That steam then rises and causes a turbine to spin fast. Once you have the turbine spinning, that can go into the electric generator, and it can convert the spinning motion into current. The current then can be delivered to houses, for instance, which are known as the load, right? That's what the generator is powering. And when the generator is delivering current to the load, to the houses, there's a magnetic force acting on the coils. That means the coils themselves that are turning in the electric generator feel the impact of adding a load to the supply. We don't get free energy. We can take a closer look at that. This magnetic force that the coil experiences gives rise to a counter torque that opposes the rotational motion. This is like Lenz's law, right? If you get something spinning, then there's going to be something that opposes that change. So here we have the shaft spinning around in the magnetic field. And the top-down view is that as it's spinning, right, in this counterclockwise direction, there's a force on the current that's opposing it that would create a torque acting against it. And we can quantify how much there is because that counter torque will produce its own back EMF, a resistance EMF. So the back EMF generated by an electric motor. When a motor is operating, two sources of EMF are present. One is the applied EMF, which we just note with V, that provides current to drive the motor. This is the one that we're most familiar with, that we know. But the other one is there's an EMF induced by the generator-like action of the rotating coil. And this one we'll note with the EMF symbol. So when we have the applied EMF that powers a motor that, sends a current to get something spinning, it has its normal voltage, right? There's a plus and a negative sign that creates a current, and that can cause the rotation. But the AC motor, in response, will create an EMF in the opposite direction. So notice there's this effective EMF inside that has a positive polarity on the same side as the other one. So it's trying to create a current going the opposite way. Some sort of like induced current. It doesn't actually create this current, but that's what it would create if there was no applied EMF in the first place, V. So this induced EMF acts to oppose the applied EMF, and it's called back EMF. So that the net EMF is the difference between them, the applied EMF minus the induced EMF. And that will affect how much current you have. The current will be the difference in the EMFs divided by the resistance. And this makes a significant difference in the motor's operation. Let's see an example of this. Example 12, operating a motor. The coil of an AC motor has a resistance of 4.1 ohms. The motor is plugged into an outlet where the voltage is 120 volts RMS, and the coil develops a back EMF of 118 volts RMS when rotating at normal speed. The motor is turning a wheel. Find A, the current when the motor first starts up, and B, the current when the motor is operating at normal speed. All right, so we're trying to solve for current here. And we know a few things, right? We know the resistance R, so that is helpful. We also know that the outlet provides this voltage of 120 volts versus the back EMF of 118 volts. So I'm going to label the 120 volts, that's our applied voltage coming from the outlet, versus the 118 volts is going to be the back EMF. Now this back EMF occurs when rotating at normal speed. And normal speed does show up in part B when it's operating at normal speed. So that one, we have a back EMF. But in A, it's when the motor first starts up. When the motor first starts up, how much is it rotating? It's not rotating. If it's not rotating, there's no back EMF because the EMF only occurs as a result of that rotation. So the back EMF is 0 when it's first starting up and it's not yet moving. This greatly impacts how much current there is. If you take a look, then we have the current is equal to the applied voltage minus the EMF. So 120 minus 0 divided by that resistance of 4. This is a current of 29 amps. That's a huge amount of current. Versus once we get the back EMF in place, once we're operating at normal speed, the back EMF is 118 volts. So the net current is 0.49 amps. It's not even half an amp. Why is this? Well, if you think about the motor, when it first starts out, to get it spinning, to get it up to speed, that requires a lot of work. Once it's spinning at normal speed, it doesn't require a whole lot of work to keep it spinning. That's, you just have to overcome any friction, right? But you're just keeping it going. And the current reflects that. When it's a lot of work to get it going, you need a lot of current to get that motor turning. But once you get the motor turning, it doesn't require anywhere near as much current. So there you have it, a look at the electric generator, which also helps us better understand the electric motor. Pretty nifty.